So it turns out that the density of water, you guys see that chart? Can you see that chart, Virginia? No. Okay. How about now? No. Awesome. Okay.
Wait, yes, I can.
Okay. So
Sorry.
it's all right. So the density of water is the first line there. It is measured in, you can measure it in grams per cubic centimeter, pounds per square cubic inch, pounds per cubic foot, or pounds per gallon, depending on what you want. So water is about, it's rounded here, 62 pounds per cubic foot. And if you ever wondered, like, how much does a gallon of milk weigh, or how much does a gallon of water weigh? It's a little over 8 pounds. So it's sort of something to keep in your head. The next one down is aluminum. So aluminum is 169 pounds per cubic foot. You go down towards the bottom, mercury is almost 850 pounds per cubic foot. The gold, even more dense, it's over 1,200 pounds per cubic foot. So if you're thinking about robbing a bank by stealing gold bars, I would not recommend it. That is not the right way to make money. And don't do crime anyway. So let's see.
I'm pretty sure they're like 23 point something pounds per bar.
Is that it?
No, in terms of in the treasury.
Yeah. Okay.
Like 23 point something per bar.
So that means you could fit like 60 bars in there, maybe roughly 60 bars in a cubic foot. It's heavy. Let's just say there's easier ways to make money. And by the way, as far as crimes go, they're like one of the worst things to do is to rob a bank. So don't rob a bank if you think there's money, because A, they don't have as much money in there as you think they do. B, it's hard to get in. They've got a huge amount of security, and the chances of getting caught is very high. So, you know.
Gold bar is 12.4 kilograms.
If you ever want to know like the best crimes to do, just let me know. I'll deny that I told you, but robbing a bank is one of the dumbest ways. So.
Do from experience?
No, of course not. What are you talking about?
Practicality.
Yeah, that's right. You gotta be practical. You want to rob a bank? You want to hook your car up to an ATM and take off? Does that ever work? I don't know. You're gonna lose a bumper at least.
Yeah, a bar is 12.4 kilograms per bar.
Okay, yeah. There's a great, you guys ever want to watch a great show? It's the old Twilight Zones. There's a ton
I remember that.
They're all black and white, of course, but you know, it's because the world was not color back then. So there is one about them stealing all this gold and then getting in this like cryogenic chamber for 100 years in the future, and they're out in the desert, and gold ends up being worthless 100 years from now. So they were double dummies on that one. So anyway, all right, let's do one where we want to use calculus because we don't want to just be boring like center mass.
So would we be getting any questions of doing with fluids other than water?
I mean, if you do, then the only thing that changes is that number right there. So I think there's some examples where it uses concrete, but if you wanted to use mercury or gold, turn that to 1200, and really that's it. So that's not the part that's tricky. The part is sort of like the depth versus the area calculation. So this is actually example 7.6.2. So suppose you have a triangular plate, which is just 4 by 4, and you want to submerge it underwater. So I don't know why I just didn't draw that. So if you submerge it so that the bottom of the plate is 10 feet down. So 10 feet is 4 across the top, 4 high. Then the question is how much pressure is there exerted on the plate? And it is vertical, so you can't just use a basic just multiply density times depth times area. Because the problem is the force on the top of the plate is different than the force that there is on the bottom of the plate. The nice thing at least is that the force will be an integral of the density, that's not too hard, times the depth times the cross-sectional area. And I've written it sort of like this. So it's right. And then dy. Well, I'll write it like this. So that what ends up happening is you'll have an integral of the density times some depth function that is determined by y. And then the area will be like a length times a width. And so it's going to be the length, use an L here, times the width will be dy. So it kind of looks like this. You need to find the depth of your strip and the length of your strip at that point. And then you'll integrate it. The reason I'm leaving off the bounds is that the bounds will depend on where you put the x-axis in order to calculate it. And now we have a couple of possibilities, I suppose. You can put the x-axis at the surface of the water. You can put the x-axis at the bottom of the object. You can technically put the x-axis wherever you want, and then the dy and the ly will change. So the delta part's always going to be 62.4, and that's fine. And you can just multiply it on the outside if you want. But the bounds, the d and the l, you have to say, I'm going to set my x-axis here, and then I'm going to work off of that. So the first part that they do in this one is they say, let's let the x-axis be at the surface of the water. So that means I'm putting my x-axis, I'm putting my y-axis. The object is down here. And if it's 10 feet to the bottom, then that means that this is at -6 and this is at -10 as far as the y-axis is concerned. This is, you made a choice that the x-axis is at the top. So the depth of 6 down, corresponds to when y is -6. And the depth of 10 corresponds to when y is -10. So if you do it this way, where you always put the x-axis at the surface of the water, then the formula becomes really nice for depth. The only thing you have to then figure out is L, and you'll be done. So if you do it this way, then the formula will always be like this. The integral from the bottom of the object, which is at -10, to the top of the object, which is 6. So we're adding up. We have the density of 62.4. The depth will always be the opposite value of whatever y is. So if it's 6 feet down, y is -6. If it's 10 feet down, y is -10. 8 feet down, then it's -8. You take the negative of whatever the y coordinate and that gives you b. And that part will always be true no matter what the shape is, as long as you put the water line at the x-axis. You'll also have dy. This is the difficult part. Can be, I mean, it's the most difficult, even though it's not always difficult. It's at least the most difficult part, is to find the equation that represents how wide your strip is at that particular depth. So if you knew y, what is the width of that thing right there? And now, I don't know if any of this stuff starts to look familiar, but you're like, wait a second. When we did this for area between curves, I took the right curve minus the left curve. When I did revolutions for washers, I took the right curve and then the left curve. And when I did this for shells, it was the right curve and the left curve. So what that means is I need to know what these equations are of those curves. So I need the equation of those lines. So what are the equations of those lines? So let's call this like L1 and this one is L2. So the equation of line 1 and line 2. And we'll do it the easy way first. Just y equals mx plus b. So y equals mx plus b. So I'm going to fill in what the slope is. And what is b? Well, the way that's because I've set it up this way. The b is the y-intercept. So for both of those lines, the y-intercept is -10. The question is what are the slopes of those lines? Well, you look at your little triangle here. It goes up 4, and it either goes over 2 to get to L2, or it goes back 2 to get to L1. So the rise over the run. So for L1, the rise is 4, but it goes, or you can think about it, it goes over 2 and down 4, or it goes down 4 and over 2. In either case, that slope is -2. And that should make sense. It's negative because the line is going down. The other one, maybe now I have the picture already. So the rise is 4 and the run is 2, and therefore that slope is 2. So 4 over 2. So one is negative, one's positive. They both pass through -10. And the L1, this is my left curve, and this one is my right curve. And on the picture, that sort of makes sense. The right side is L. Did I reverse it? Yes, I did. I think the problem is I wrote them backwards. This is the left curve. So yeah, L1 is the left curve. L2 is the one that's on the right. So I'm going to want to subtract that. The only problem is that everything has to be in terms of y's. And right now, everything is in terms of x's. So all I got to do is I have to solve for x, and then I can do right curve minus left curve. So that's on the next slide. Solve for x in those two equations. So again, L1 was, which means that's -2x minus 10, and L2 was y. Let's get the eraser here. Y equals, and y equals 2x minus 10. So solve for x. So you bring the 10 over, so that'll be y plus 10 divided by -2, and that'll be x. On the first one, that's line 1. Line 2, you bring the 10 over, add it, and then divide by +2, and that gives you L2. And again, L2 was the right curve, this is the right curve, and this is the left curve. So to get that entire length here, I will take the right curve and I'll subtract the left curve. So my length formula will be the right curve minus the left curve. So what do you get there? You get y plus 10 over 2 minus y plus 10 over -2. And if you look at the fractions there, that's y plus 10 over 2. If I do minus a minus, that'll be another y plus 10 over 2. So it'll be y plus 10 over 2 plus y plus 10 over 2. It'll be 2y plus 20 over 2, or just y plus 10. So if you knew the y coordinate, you just add 10 to it, and that will tell you how wide this is. So again, also then my cross-sectional area would have been just multiplied by delta y. So anyway, if I put that in the formula, I get that the force is equal to the integral from -10 to -6 of the density, 52.4, times the depth. So it's density, depth was minus y, and then the area would be a combination of y plus 10 and delta, and dy. Because it's length and width. And boom, that's my setup. So these are just like the stuff from 7.5. They are not short. They're definitely not short. And if you work that out, it's around approximately 3,661 pounds. So that's how you do if you put the x-axis at the surface of the water. We're going to do that again. We're going to put the x-axis at the bottom of the object. And the answer will still be the same. We'll still get 3,661 because we're still talking about the same setup. We've just moved our frame of reference on this problem. So we still have the water. We still have our object at the bottom. But now I'm going to put the x-axis at the bottom of the object. So this is like method 2. And you can decide which one you like better. So put the x-axis at the bottom. So now, what's the setup? So that means that this is at 0, this is at 4, and instead of being at -10 and -6, I'm working, it's 4 high, and then this value up here is 10. So that means when I put my little strip in here, then the y values are now going from 0 up to 4 for dy. So the bounds are 0 and 4 instead of -10 and -6. Now what's going to end up changing is the d equation for the depth and the length equation for the strip. And they'll like kind of balance. One will change by a certain amount, and then the other one will pick up the slack. So that when you work up the integral, it'll give the same answer. But anyway, the force is always the integral of the density times the depth times the cross-sectional area, which is like length times dy. So density is the same, 62.4. What is the depth equation? So let's see. Come over here, and you're kind of like, if y is 0, if I'm right there at the bottom, then the depth is 10. So I will be 10 units down if I'm 0 units from this x-axis. If I'm 1 unit from the bottom, then my depth is 9. If I'm 2 units from the bottom, then my depth is 8. And if I'm 3 units and so forth, whatever the y coordinate is, in order to get d, I take away the y coordinate from 10. So the depth equation now is 10 minus whatever y is, and that's going to go there. Now, what is the length equation for the strip? We have to draw the strip according to my axis here. I want to know how far across it is to get the length now. So the length will still be the same thing. The length will be the right curve minus the left curve. The problem is now those equations are going to change because you've moved your axis system. So we have to figure out the equation of this line, and we have to figure out the equation of this line. And they're actually much easier because they all go through the origin. So what is the equation of this line? Well, it's just y equals mx plus b. But what is b? It passes through the origin, so that the intercept is 0. The slope is 2 because it still goes up 4 and over 2, so it's still 4 and 2. So it's 2x, and that's it. And what's the equation of the other one? Well, it's the same, but it's like negative slope, so that's negative 2x. So that's the equations of those lines became easier because of where you put the axis. The depth equation got a little more complicated. So what are the right and left curves? We now have to solve for x on both of them, and we'll get y over 2, and we'll get y over negative 2, or negative y over 2, however you want to do it. So that'll be y over 2 minus a negative y over 2 will be my length equation. And that's just y over 2 plus y over 2, so that's equal to y. And that's going to go in. Okay. So if you are 2 units up, it's going to be 2 units y. If you're 4 units up, it's 4 units y. Whatever the y coordinate is tells you you're there. And now that's the set. Density, depth, length times the width of dy. And that setup will also give you 360. So there's those two. How about, can we do this with center of mass? Let's see. So again, forget the axis system just temporarily. I know that this is 10 to the bottom. I know it's 4 across the top. I know it's 4. So if I try to do center of mass with the force should be the density times the depth of, let's call this like COM here, the depth of the center of mass times the area of the plate, the total area of the plate. So without having to do any integrals, this is nice if you can figure out the center of mass. So this is 62.4 times the depth of the center of mass, which I don't know, times the area of the plate. And what is the area of the plate? Well, it's a triangle, and it's 4 wide and 4 high, so that area is going to be 1/2 the base times the height, which is just 8. So, use my calculator real quick here. So we'll do 62.4 times 8, and then 1, 2. And in order for this to work out to be 3,661, this number here has to be 7 1/3. Now, does that make sense? Let's see if you know what the center of mass is right in the middle. The center of mass of a square is right in the middle. The center of mass of a rectangle is right in the middle of each one. What is it for a triangle? You know where the center of mass of a triangle is like this? Well, according to this, that means that this has to be, this is 6, which means in order to get to the center of mass, I need another, how much? I need 1 1/3. And so this is broken up into 6 and 1 1/3, or third, and 6 4/3. And this is maybe where if you haven't seen it, it will be in engineering tables. And if you want the center of mass for an isosceles triangle like this, it's exactly 1/3 of the way up from the base. And so that is 4 high. You take 1/3, you get 4/3 added to the 6th, and you multiply that by 7 1/3. And that'll work also to be the same out. So if you know the center of mass, you don't even use calculus. You just find the area of the plate, multiply by the center of mass depth, and multiply by the density, and then you got that. So that's pretty much how you do those problems. There will just be lots of pictures. Maybe we can try one more and then see if you have questions about other stuff here. So this is number 14. I don't remember if it's a homework problem or not. It doesn't really matter. Suppose that you have a container and you fill the container up with either water or concrete. And so the side of this container, this is 4, and the curve is y equals x squared. So how much force is there on the side? So maybe this is like some long trough and you have these things on the side. How much force is on the side of the object? Now I definitely don't know where the center of mass is. So I'm going to have to use these ideas that my force is going to have to be some integral of the density times the depth equation times the length equation dy. And those will depend on where I put my axis set up. Maybe I'm just going to do it one way, and then we'll see if you have questions about previous stuff. So I'm just going to do it where you set up the x-axis is at the top of the object, because the depth equation becomes really easy. So I'm not sure I do actually, because I know that y equals x squared. So if I put this at the top, I'm going to have to then figure out what that new set of equations is. All right, I lied. Let me take this out. Let me put it at the bottom. Just because I've got the equations already nice and set up for this. You can try it at the top and see what happens. It makes the D easy, but the L hard. If I do it at the bottom of the object, it'll make the L hard, but the D will be a little bit harder. I don't know. I think the D doesn't become as much harder as the L becomes easier. Anyway, so if I put it at the bottom of the object, the x-axis, so this thing looks like this, then I know that my integral will go from 0 to 4 because I'm going from y equals 0 to y equals 4. I know that my delta is, well, I'll have to put that in a second because there's two parts, whether you're using water or concrete. The D, we've already seen that, again, the depth is going this way, the y is going that way. So if you know that the D and the y kind of have to combine to get 4, and so if you knew the y coordinate, then the depth would be 4 minus whatever that is. And so that becomes your depth equation. The width equation, well, what I have to do is I have to figure out what the equation of these curves are. We know that we have the parabola y equals x squared is the base, but just like we did on the others, let's solve for x. What happens when you solve for x? Well, you're either going to get the positive square root of y, or you're going to get the negative square root of y. And this is good because y equals the positive square root is the right side of the parabola. That's like the right map of the parabola. And this is the left side of the parabola, the left map of the parabola. So just like I've been doing up to this point, I take the right curve minus the left curve, and I'll get the square root of y minus a negative square root y, which is 2 copies of square root y. And so that's going to go in there. 2 copies of square root. And so that's my equation. Okay. And in problem 14, all you do is you just work that as part A, where the density is 62.4. In part B, you work it out where the density is 150. And really, that doesn't matter because you just, it's a constant. So you can even just pull the constant out, figure out what the integral is, and then at the end, multiply by the density. Or plug it in and work it out. But this is super easy. Just, yeah. But anyway, that's kind of like, that's how you just work it. And with that said, let's see if you guys have homework questions about 7.5 or anything before that.
Actually, a question on number 20 for 7.5.
Okay, so you have a tank, cylindrical, 5 meters tall. It has a radius of 2. It's only filled up with 3 meters height of whatever your liquid is. And the density of that is, it's gas apparently, so 737.22 kilograms per meter cubed. Compute the total work in order to pump it out of the tank. So what is the work equation is just the integral of the force. Basically, it's the integral of the force. And since we're doing it this way, we're going to need our cross-sectional areas to be in terms of y. So we just sort of have to figure out where we're putting it's where we put our axis system again. I think that in the examples, we often will orient it where y equals 0 represents the base, sometimes it represents the top. So I don't know. Which way did you try it? Or did you?
Sorry, I was saying I originally did the first way. I was trying to go from top to bottom instead.
So the axis is where? Where is it? At the top or at the top?
Yeah, I went for the top instead.
Okay, so suppose that we put sort of like that, and we have to pump the fluids up to the top of the tank. So that means that my x-axis here, the bottom of this is going to be what? It's going to be when y is -5,
Right.
and the top is going to be -2. So I get -5 to -2 is where the fluid is, and therefore that's the range of where my cross sections could possibly be.
So -2 or -3?
-2 in this instance.
Yeah. So it says that you have 3 meters worth of fluid, and so you're down here at 5. You go up 3. So -5, you can stop at -2. If you stopped at -3, that would mean you only have 2 meters worth of height of fluid. That makes sense?
Yes, sir.
Yeah, that makes sense.
So -5 to -2. And then, what are the pieces that go into this? As you look at your sort of cross-sectional area of all of these things, you're going to have the density. And, in order to make all the units work out, this is annoying, right? You're probably going to have to stick in the 9.8 in order to make this work out, in order to get into like Newton meters. So you got this, you got 9.8 in there. And then any sort of cross section in here is nice because at least it's just a little disk in here. So that guy right there is like, what's the volume of that? It's pi r squared, but r is always 2 times the height, and that's where the dy comes into play. So you just take that and substitute it here. So the integral becomes a lot easier than that conic section one. Yeah.
And then you stick on an X to the end of that, right?
Well, let's see. So then we have to talk about, so now we then have to talk about like how far are we moving it? And so that's just the like the volume part of it. So this would be pi times 2 squared. The delta y becomes dy. And then the final thing is like how far are we having to move this little strip? So if it's at the bottom, we have to move it 5 units. So it's like the distance moved again versus y. If you're 5 units down, then you have to move it a total distance of 5. If it's 4 units down, then you have to move it a distance of 4 total to get it up the top. And so you can see that the distance equation is always whatever the opposite of the y coordinate is, because you put the axis system at the top. Now, this will work out because we've got minuses here and we've got minuses here. So when you work this all out, then you'll get some like positive number. Again, its work is like force times distance. This would be so. Can we just do this with like center of mass as well? I bet we could. I bet we could do this problem by just saying, let's see. So I want to take the force, so that would be 7.22 times 9.8 times, what's the volume of this stuff? The volume of the liquid is, well, it's pi r squared h. So it's pi times 3 squared. The height is 3. So that's like the whole volume of it. Now, how far do we have to move it if we use center of mass? Well, where's the center of mass of the gasoline? How far down is it? And maybe not too surprising, it's halfway between. So what's halfway between 2 and 5?
I'm sorry, could you repeat the question? As my broke up a bit.
How far is what's halfway between 2 and 5?
3.5.
There we go. So we can just multiply it by 3.5. And that answer would be exactly the same answer as what we got at the beginning. Magically.
So when you're doing these problems, do you always have to include gravity?
If it is in English units, it'll be given as pounds, and the 32.2 or whatever is included in that. If you're doing metric, then gravity is not included in
Okay.
Okay, thank you.
that.
What about okay, just curious, what about problem number 24? That one I have some bit of trouble with too.
Okay, so what they're going to do is they give you the tank. Let's see, so the tank is now conical. These are harder because it's not a uniform cross section all the way down. You've got these teeny little cross sections at the bottom and big cross sections at the top. It's 5 meters deep and it's 3 meter radius on top. And you fill it with water, and now, since the density of water in metric is the point of metric for water is it's 1 kilogram per cubic meter. Sorry, not one. I hope that would be good. So it's 1,000 kilograms per cubic meter. Cubic meter is big. You know, it's like over 9 feet by 9 feet by 9 feet. It's 1 gram per cubic centimeter is the point for metric. Okay, so it's filled up with water. Now the parts are, we want to either pump it to the top of the tank, or we want to pump it to a point where our pump extends out a little bit, so we're actually shooting it maybe over a fence or something. So we need an extra 2.5 meters. And then the question is if you just took the top half of the tank by volume, and you wanted to just pump that part out. So the top half of the volume versus the bottom half of the volume. That's going to be tricky because you're going to have to figure out like where is the point, like the top half. This is like a little bar trick. You guys probably aren't old enough, right? But if you had a martini glass and they said, all right, fill it up halfway filled, then where is the line? Like if you had to make a line on the side of the glass so that it would be halfway filled with fluid, where would that be? So think about that. It's not halfway, right? You said, well, I'm just going to make a line halfway between here and here. Well, clearly there's more on the top and middle than the bottom. So you have to figure out where that is. So when you turn 21, you can do that. All right, so this is very similar to one we did in class. If you said part A, I want to just do it to the top of the tank. And I think when we did that example, which way did we do it? I think we put it at 0 is ground level. Yeah. So we want to pump to the top, and we're then going to put the x-axis at the top. I think this will work out nicely. So in order setup, maybe just look at it from the side. Here's our x-axis, here's the y-axis. It's 3 units to the top at the top of the tank, 5 units to the bottom, so that's technically y equals -5. And so when we work this out, the work will be, I think we did this before using, before we did this using pounds and feet. But anyway, if we set it up this way, then we know for sure that the y values are going from -5 up to 0. That's where the fluid lives. And then in dy. So we have density, which in this case is going to be 1,000. Got our 9.8 in there. There it is. Then I have to figure out the 2 parts where it's like, get the rest of the volume. It's going to be like pi r squared, and then the dy is like my 8. Then the depth. So this is really like, it's going to be like pi times the length times the radius of my object squared, and this is kind of like my height. So those 2 things together can give me like the volume of when I do my little cross section here and spin it, it actually is like a little cylinder. And it's an approximation. I mean, these things are slanted, the cylinder isn't, but again, we're doing a Riemann type process. So all I need to know is I need to know, like, how far is it from there to there? If I knew y, how far is it over? That's one. The depth is, again, I have to do this like equation. So let's see. If y is -5, then the depth is 5. So if I'm at the bottom of the tank, then 5 units down, but y is -5 because of the axis system. So this is going to be the negative of 1. The cross-sectional thing is I need to figure out, and you can do this with similar triangles. You know, it's 5 by 3, so you could probably figure out a nice little similar triangle. Or if you don't want to do that, you can just find the equation of that line. So what is the equation of that line? Well, it's y equals mx plus b. So y equals whatever the slope of that is, x, and I already know b is -5. So b is -5. What's the slope? Well, it's positive, and it goes up 5 and over 3. So 5/3. 5/3. Yeah, 5/3 x minus 5. But again, it's side to side, so I have to solve for the martini glass here. I have to solve for x. So x will be, bring the 5 over, y plus 5, and then I divide by 5/3 or multiply by 3/5. And in the picture, the x coordinate is exactly the radius of my thing. So if I go over x, that's exactly r. So x and the radius of the strip are exactly the same. So this would be 3/5 y plus 5 squared, and then pi in there somewhere. So I'm going to stick pi in. I'll put it somewhere. I already made my squares. And I'm going to put it here. Pi. That pi I just stuck out. No. And that's the setup. That's the setup for part A. And they're not short, they're not easy for sure. But it really comes down to density, gravity, the radius of your strip times the squared, then times the depth of the strip, and then the pi comes in because it's the cylinder. So that's part A. Part B is I want to find the work in pumping the top 2.5 meters to the top of the tank. So it's exactly the same equation, except y is now not going from -5 up to 0 because I only want to talk about the top. So the only thing that changes in part B is it'll be from -2.5 to 0. And everything else stays the same. So the density is the same, gravity is the same, still got pi times 3/5 y plus 5 squared. The depth equation is still the same. And that's it for that. The final thing is the work for pumping the top half of the volume out is I go pi, everything else is the same. 1,000, 9.8, 3.5, or 3 divided by 5, y plus 5 all squared. Everything is the same. The top of the tank is at 0. The question is how far down do I go in order to say that half of the volume is in that range and the other half is at the bottom range? So how the heck do you do that? How do you find where that is? Any guesses on that? How do you do that?
Is it a third of the way, like the center of mass thing with a triangle?
That would be nice. That would be nice for sure. Let's see. So this is 3, and this is 5, and yeah, and technically it's a cone. Then the volume of the entire thing is 1/3 pi times the radius squared times the height. I don't know if you ever thought about that before, but if you drew a cylinder and you drew a cone inside of it, like that, the question is what percentage of the volume in the cylinder is made up by the cone? And the answer is exactly 1/3. Because the outside, the cylinder is pi r squared h. The cone is 1/3 pi r squared h. So it's exactly 1/3. So the volume here will be, let's see, 9 times 5, that's 45 divided by 3, 15 pi units squared. So the question is can I work backwards off of that? How would I get 7.5 pi? And really, I mean, if we knew that this was half of the volume up here and this was half of the volume down here, then maybe it's easier to figure out this part here. This would be like a smaller cone which has volume 7.5 pi, so half of that. So what are the dimensions of that smaller cone in order to get this? Well, I know that that's supposed to be 1/3 pi, whatever that radius is, and whatever that height is. There's the h and r. So this is like my new one. It's the new radius squared and the new height squared. So crap, I have to work that out so that it's 7.5. But now I have two things I don't know. I don't know r and I don't know h. So how do I deal with that? Well, the cool thing is this is a similar triangle kind of idea. Is that maybe draw too many pictures on the board, but like this. If this is 3 and this is 5, and this is h and this is r, how do you do similar triangles on that? Do you remember? So it's a ratio of things like h is to r as 5 is to 3. So if you knew how far you came up from the bottom and wanted to go out to the edge, that, and you try to figure out which, well, it doesn't probably really matter which one I solve for here. The height is exactly 5/3 the radius, so I'm going to stick that into my equation here. So that's the relationship between the height and the radius using similar triangles inside of the cone. So I get 1/3 pi. I'm going to drop the news too, and then drop. So that's r. This is 5/3 r. And now crap, I'm going to have to multiply back out anyway because I really wanted to know h, not r. So maybe I should have solved for r. Maybe it's the same difficulty. So that's supposed to be 7.5 pi. So solve for r. So cancel pi. So this is 5/9 r cubed is going to be 7.5. So does this work out nicely? R would be 7.5 times 9. That's 15 halves. Oops. So 7.5 times 9 divided by 3. Take the cube root. That's 2.82. So around 2.8. So right, so R would be, let's see, was it 7.5 times 9 divided by, whoa, 7.5 here. 7.5 divided by 5. Oh, did I do that right? Yeah, I did. So R cubed is 13.5. So R is about this. So what's H? H is 5/3 of that. 5/3 of around 2.2. I did all this right. I can now split it up. Times 5 divided by 3. So 3.97. So it's 3.97 from the bottom, so it's like 1.03 from the top here. So my integral would only be the integral from, well, how did I have it set up from the top? Yeah, from negative 1.03. Or maybe you can think of it as 5/3 of the cube root of 15 times 7.5. Oops, hang on. Yeah, 715 has, no, 13.5. 13.5, 27 rounds. So that's the only, and that'll be minus. Figuring out where that is. Hopefully I didn't make a mistake. It would be nice if it was 1/3 from the top. I'm not sure that that's the case. That's the center of mass for a triangle, but then you're revolving lots of things. So, I don't, I'll double check that I didn't make a mistake there, but that's the basic idea is where is the fluid, density times gravity, the radius of your strip times the depth. And if you put the x-axis at the top, this will always be, d will always be negative y. So the hardest thing you have to find is the radius part. All right, what other questions? Or now you're like, I don't want to ask any more questions. Those are too hard.
Well, I'm sorry, can you go back for a minute? I just want to check C. See if I got it correct. I'm sorry, is that a 7 for the integral for C? Is that a 7? Is that 27 over 2?
Well, yeah, it was 13.5.
Okay.
So, I mean, I'm going to have to work this back out myself. It's possible that I made a little mistake here. Because according to this, it's not a third. It's supposed to be a quarter of the way up. But I'm wondering if that is for a specific one. Yeah.
Okay.
Maybe
Okay. I think I got it, but I had definitely had a few more errors I thought I did. I just want to clarify that. Thank you.
Sure. Okay. Let me think about that one more. But at least we know that the answer is going to be the same stuff because it's all the stuff in the middle makes sense. It's just where is that location at that point, so that half the volume is above and half the volume is below. And that might be different, but the same thing as center of mass should be. Maybe not. Anyway, all right. Any other questions we got?
Number 16, 7.5.
Okay, so the nice thing about springs is you've got this equation that the force on a spring is the spring constant, which is just a characteristic of a spring. The higher the spring constant, the greater, like the stronger. And then x is the distance that you've stretched it off of its natural length. So they usually sort of draw like, that's not a resistor. Got a spring that's a certain distance, and then you stretch it. So this is like the natural length. And then X will be how far you either stretch it or compress it off of that. So it says that a force of 7 newtons stretches it from 11 centimeters to 21 centimeters. So 11 is the length. You stretch it an additional 10. So, but remember, this has to be measured in newtons. This has to be measured in meters. So it's K. It's not times 10. It's times 0.1 because it's 10 centimeters and that's 0.1 meters. So I don't know if that made a difference, but that means that the K is 70. So I guess technically it's like Newton per meter. So the work on these is just the integral of the force. So in this case, we have the integral of 70x because it's just K is 70. And how much work is performed in stretching from a length of 16 to 21? Well, does that mean an additional, or does that mean like it goes like this? It's like this is 11, which is the natural length, and then you stretched it out to 16, but then you stretched it from 16 to 21, and I only really care about the work on that. If that's the case, then this is 11, but the X value is going from 5 to 10 centimeters because it's based off of that original 11. So it's 11, you stretch it out to 16, you did a certain amount of work, but we don't only care about now. What about the work from 16 to 21? You know, we could figure this out in actually just 2 ways. We call this one work 2 and work 1. It's not a bad idea. That work 1 will be the integral from 0 to 0.05. Because again, it's 5 centimeters. You have to convert that to meters or else the units are of 70. The work here, work 2, is going to be from 5 centimeters to 10 centimeters, so 0.05 to 0.1. Which is, I mean, it's a good thing to point out. If you stretch it from the base to 5 units out, that's the first one, 5 centimeters out. From 5 centimeters to 10, you get this. Now, should that be the same answer? Like, they're both 5, but the problem is you've already stretched the spring a certain amount, and now you're stretching with more off of that. So it really wants to try to come back more. So when you work this out, you know, one of these intervals is going to be different than the other. The second one is going to be larger. It's more work to stretch it even further because it wants to pull back more, depending on how far you are off. I hope that sort of makes sense from your life.
Yeah, that makes sense, sir.
For this particular problem, it's the one you're talking about is the second. That's the actual one.
For this problem, there are 2 instances of work, not just
No.
from. Okay.
I mean,
'Cause I only,
technically, it starts at 11, and the problem
Okay.
is how much work would it take to stretch it from 16 to 21? So you kind of skip over this first one, you're pulling it to 16, and then you pull it from there. So there was some work that happened to get it to 16, but we don't. I mean, the homework question didn't ask for that.
Okay, so what's being established is you're just basically, in this instance, you're just taking the work I already did from 11 to 21 and then just subtracting it or just including it with the 1621 or subtracting basically.
I mean, the answer to the homework problem is just this, because 16 centimeters out is really 5 centimeters from the end of the regular natural length. And 0.1 is 0.1 meters, which is 10 centimeters, which is actually 21 centimeters if you are talking about, from the base. Yeah, this 11 is the spring itself, then you're stretching it off of that.
Okay. Also, because we're 16, I had the 5/100s I had from going from 0 to 5/100 instead of from 0.5/100 to 0.1.
Well, that's what I'm saying is if you went from 0 to 5/100, that would be stretching the spring from its natural length of 11 to 16, not from 16 to 21. They are different.
Okay.
Yeah.
Okay. I just wanted to clarify that.
Yeah.
That does make a bit more sense though.
Yeah, I mean, with a little tiny spring, you probably can't tell the difference. But if you have a big spring and you stretch it an inch, it takes a certain amount. And then from there to 2 inches, it's harder. Just because the spring is really trying to press itself back even more. And that's the whole point of Hooke's law is the force that you will have really depends on like how far off you are stretching it from its base length. Unless you totally deform it, you know. You took the spring and just like pulled it into a straight line. We're assuming that there's no like actual deformation of the spring, which could happen in the real world, in which case Hooke's law, you throw it out the window and this simple equation doesn't work anymore. And you really would like to not have that happen. In your car, you'd like for the spring to, once you stop driving, to go back to the original. If it gets stretched or compressed, then you have to change, you have to get a new spring.
Okay. I understand.
Any others, or you guys want to go work on stuff?
Can you work out number 14?
Okay, so it really is kind of the same idea as, you know, force equals kx. We're dealing with pounds here, so this is 50. Spring constant I don't know, and you're stretching it. I mean, you're compressing it, and the thing is compressing the spring versus stretching the spring is effectively the same. Thing. So when it says compress versus stretch, I mean, really, you can think about this like it's a half. And it's from 18 inches to 12 inches, which is a 6-inch, but you need to convert it to feet. So that's 1/2 of a foot. So when you're working this out, then, you know, you bring this over, your spring constant is 100. So when you do the work, then you're integrating 100x, or not 1,000, 100x. Now, what are the bounds? You could work them out to say, well, technically I'm stretching it from 0 to -6, not -6 because it's 6 inches, but -1/2 foot, versus saying, well, no, actually, you know, it's like, what about just saying 0 to 1/2? You know, is there any difference between like compressing the spring by 1/2 foot or stretching the spring by 1/2 foot? And the answer is both of these things, you're going to get the same thing. You integrate this, you get 50x squared, and you put in the bounds, and you'll get 50 times 1/4. Well, if you did the same thing down here, you'd also get 50 times 1/4, and therefore it doesn't matter if you're thinking compression versus stretching, as long as it's off the natural length.
Is it 0 to -1/2 or -1/2 to 0?
Well, that's the other thing to think about. What happens if you went -1/2? Well, I mean, because technically, what is x doing? X is going from 0 to -1/2.
Honestly, I don't understand how you could get -1/2 initially, because instead of expanding outward, so I thought that means it was increasing in length, so it was being pulled outward, so it had to be a positive.
Well, the problem says you're compressing the spring. So you are technically taking the spring, which at the base level is 18 inches, so 1.5 feet. and then you're compressed. So this is kind of like x equals 0, right? The x is always starting from the natural length of the object. So if you took it and you compressed it down so that it was now at 12 inches, then yeah, this is what? X is -6 inches or -1/2 foot. And so if you did you're going from 0 to -1/2 that's the, if you went, well, wait a second, really, it's like, what's the difference between going from -1/2 to 1 or -1/2? In an integral, it won't matter. You'll end up getting negative in your answer because the bounds are switched. But then you just have to interpret what that means. That you're like, what, negative work? Well, okay, that means, yeah, what is this measured in again? This is 50 divided by 4. So 12.5 foot-pounds. And so that's like the magnitude of the work. It just happened that you were sort of pushing it in versus pulling it out. I don't know, does that make sense?
So these aren't bounds. These are like it's literally what you're going to.
Well, in all of these cases, I think if you work these out, you can think of this as either going from 0 to -1/2, or you can think about it as going from -1/2 to 0, or you can think about it as going from 0 to 1/2, or you can think about it going from 1/2 to 0. All of those end up giving you either 12.5 or it gives you -12.5. And then you just have to come back to reality and say, well, I know it's work, so it has to be, foot-pounds. I have to expend it. So, really it's kind of like, I don't know. Nature doesn't like you to take stuff away from it. So the point is that you could just take anything that you had, just like take the absolute value of any of these. If they end up being negative, it's because you have expended 12.5 foot-pounds of force. But they all represent the same thing from an integral standpoint.
Got it. Okay.
Okay, let's stop there. We'll say you can work on, you still need some time on this. 7.5 technically due today. Hopefully you can get it done. 7.6 will be pushed back tomorrow or Monday or something. Not a bad idea to get as much as you can done before the weekend because they're all not too bad. They're all not too bad. There's not that many of them. And it'd be nice to start chapter 8 fresh in your brain. But I'm not going to be too big of a stickler as long as if it's a day late or something like that. It may take me a while to catch up. I think I now have like 20 different homework assignments that I'm looking at and people turning in old stuff. But I'll catch up eventually and I'll grade the test. And otherwise, we'll meet back tomorrow morning to finish off this week. And the next week is a couple days and then we have a test in the final. So that's where we're at. So finish strong. Put in maximum effort to get caught up on stuff. There's one more weekend left. A little pain now will pay off in the long term. So I'll stop talking now. Have a good rest of your day.